Looking at acceleration, which of course means the rate of change of velocity, not how much the velocity changes by, but rather how quickly the velocity is changing. We learned the other day now, a few days ago, that within our kinematics equations we have two groups. The first equation that we learned on the second day of class is what we call our group A equation. This is used whenever we have a constant velocity or an average velocity. Basically, whenever an object is not speeding up or slowing down, or if it is speeding up or slowing down, we're not looking at the change, we're just looking at what was the average during all this time. Maybe I drive to Edmonton and I go at 110 kilometers per hour, but occasionally I slow down because there's a car ahead of me. I want to find the average when I get there, not what I was moving at each individual point. That's a group A equation. We use that for constant or average velocity. Now, my other equations that appear under kinematics on my data sheet are what I call my group B equations. My group B equations are used whenever there's an acceleration. And what we've learned about those equations is that we don't have to worry about which one is the right equation. If we're in the right group of equations, we can't really go wrong. Right? Unless we make some silly mistake somewhere. If we're in the right group of equations, we pick group B when group B is valid, then it doesn't matter which one we try. We're either going to get the right answer or we're going to get no answer, and we just try again. So the moral of that is, the lesson that we learn from that is, just try something. As long as you identify correctly that it's either A or B, then just try something and you can't really go wrong. Don't be afraid to try. All right, we had two questions for homework on page 52, and I want to take a look at both of these questions. Number one says a jetliner lands on a runway at 70 meters per second, reverses its engines to provide braking, comes to a halt 29 seconds later. What's the jet's acceleration, and what length of runway did the jet require to come safely to a stop? Is this group A or group B? This is group B because the jetliner is decelerating, which is a negative acceleration, right? So we're going to pick from our purple equations here, the 5 of them we have, write down some givens, and then we'll see which one we try first. Okay? What do we have here given to us first in question number 1? 70 meters per second. What is that? That's a V something, right? Is that V? Is that VI? Is that VF? What is that? That's VI. That's the initial velocity of the jetliner. Now, not how fast the jetliner was moving in the sky, but the initial velocity for the problem at hand. If we wanted to analyze it coming down out of the sky, that would be a completely different problem. VI would be different, but it would be a different problem. Okay, this is VI for the problem at hand, which is the deceleration of this jetliner on the runway. All right, comes to a stop 29 seconds later. We're going to say delta T is 29 seconds. We want to find the jetliner's acceleration, and we also want to find the displacement of the jetliner during that time, because we're looking for the length of the runway. The displacement is the length of the runway, right? Notice I've put both things that I'm looking for together. Basically what I'm saying is it doesn't matter which one you solve for first, just get whatever is easiest and then get the other one. Is there anything else that we have, though, if we read between the lines here? Yeah? Casey? Good, VF is 0, because it does say it comes to a halt. Comes to a halt. Halt means stopping, right? So VF would be 0 meters per second. If it just said the jetliner lands on a runway, 70 meters per second, brakes, what's the acceleration 29 seconds later, then we wouldn't assume that VF was 0. Okay, but if it says it comes to a halt or a stop, then absolutely, there's no assumption to be made here. They're telling us VF is 0. All right, which equation looks like it applies here to solve for either A or D? It doesn't really matter which one you get first. Got VI, got T, got VF. Which one do you want to use here? Yep. Cameron? All right, that's a valid equation because it fits within our group B list. So let's try that. If it doesn't work for us, oh well. Now, this is going to, if it's going to solve for anything, it's going to be displacement, right? That's okay. So we're looking for displacement second. Who cares? Do B before A. Doesn't matter. Do we have VI? We do. We have VF. We have T. That's going to work for us. VI is 70 plus 0 over 2 times a time of 29 seconds. 35 times 29, I assume, gives us kilometer, 1,000 meters. What is the unrounded number that it gives us there? What is it? 1,015? 1,015 meters. Now, they say it's a kilometer, right? Okay, well, they're rounding it to 2 digits. If we rounded this to 2 digits, it would be 1.0 times 10 to the 3 meters. Or you could change it to kilometers and say 1.0 kilometers. Now, we started talking about significant figures yesterday. I told you not to sweat it. Okay, we'll deal with it in detail after the break. Okay, but if you're kind of familiar with them, we would recognize that this one would be 2 digits, because we always look back at our data and we see how many digits the data is. This is 2 digits. This is 2 digits. The final answer is going to be 2 digits. If we had 2 and 3 digits in our data, our final answer would be 2 digits. We always go with our least precise. Okay, there's the displacement. We just solved for B. Good. Now let's get the acceleration. What do you want to try for that one?
I was going to ask, so when we're identifying the acceleration,
Yep.
just use the 1,015.
Yes, good question. Good question. Now, we don't necessarily need that number to get acceleration. There may be another equation that will work with it, but understand that now we do have that displacement if we need it to find if we need it or if we want it to find the acceleration. But if you're going to use that number, use the 1,015, not the 1.0 times 10 to the 3. Okay, use the unrounded, always, when doing a calculation, always use the unrounded number. Okay? Jacob, what equation do you want to try there for that? Yeah, that's probably the easiest thing, right? We have VI, we have VF, we have T. Let's just say A is equal to delta V over delta T. So as it turns out, probably the easiest way of solving this question is to not use that 1,015, right? Let's try it without here. Delta V is VF minus VI, that's 0 minus 70 over 29 seconds. What does that give me? 70 divided by 29, 2.4, negative 2.4. What does the negative mean? What does the negative mean here, Cameron? Sorry? Deceleration. Good, that it's slowing down. Now, did anybody get 2.4, negative 2.4, but do it differently? Ben?
No, I got it.
Same way? Okay. Anybody do it differently? What if we took that displacement, and did maybe D is equal to VIT? How about VFT minus 1/2 AT squared? Okay, what if we did that? What if we said D is equal to VFT minus 1/2 AT squared? We know that VF is 0, right? So D becomes equal to negative 1/2 AT squared. We have D, now we do, it's 1,015. We have T given to us in the question. Could we solve for A that way? Absolutely, absolutely we could. And we should get negative 2.4 meters per second when we do that. So we're allowed to use that 1,015, but we don't have to use that 1,015. All right? Let's take a look at question number 2 now. Number 2 says on-ramps are designed so that motorists can move seamlessly into highway traffic. How many people have their driver's license here? Okay. One of the things that drives me crazy. You know what I'm going to talk about here? Oh, one of the things that drives me crazy is when I'm driving on the highway or trying to merge onto the highway or coming off of the highway, usually going onto the highway, and you see the merge lane, right? Not yield, but when you're going onto a highway, it's a merge lane, right? The idea is that you get up to speed in the merge lane and then merge into traffic. It drives me batty when I go into a merge lane and there's somebody that's stopped halfway down the merge lane and they're doing this behind the wheel, looking sideways. I can't get out. I can't. No kidding, you can't get out. People are moving 100 and you're stopped. That's why you can't get out. The whole purpose of A merge lane is to get up to speed and merge. Similarly, sometimes we're coming off the highway, right? The idea is to not slow down while you're on the highway. The idea is to go into the lane, the turning lane, and then slow down so that you're not tying up traffic on the highway. This is a merge lane where we're going into highway traffic. The idea is that on the on-ramp, we're going at 50 kilometers per hour, but we need to increase to 100 kilometers per hour in the merge lane. Not slow down in the merge lane, but speed up in the merge lane so that we're going at highway speed or almost highway speed when we go out into traffic, 100 kilometers per hour. The engine in this one can provide a maximum acceleration of 3.8 meters per second squared. How long does the on-ramp need to be? What's the minimum length there? How long does it need to be so that it gives me time to accelerate from 50 to 100? You can imagine if you're designing a highway, this might be a useful calculation to perform, right? How long do I need to make the merge lane in order so that cars can actually speed up as much as they need to speed up? All right, is this a group A problem or a group B problem? This is group B. Yeah, so let's pull down our equations here. This is a group B problem. So we're going to write down some givens, and then we're going to identify which of those group B equations seems to fit the best here. Something is 50 kilometers per hour here. Oh, you know what I just noticed? You tell me what I just noticed. You tell me what I just noticed, Rachel? Yeah, we got kilometers per hour, and we got to be in meters per second here, right? Something's 50 kilometers per hour, something's 100 kilometers per hour. Tell me what the 50 is. Is that V, is that VI, or is that VF? That's VI, the initial velocity. Demi? The initial velocity. Tell me what the 100 is. That's VF, right? Let's figure these out in meters per second right now. 50 times 1,000 gives me 50,000 over 3,600 seconds. What is that in meters per second? 50,000 divided by 3,600. Thank you. 13.8889, I assume, meters per second. 100 kilometers per hour, 100,000 divided by 3,600 seconds, I believe gives me 27.7778 meters per second. What else we got here? The maximum acceleration is 3.8. We're speeding up, so we're going to make it positive 3.8 meters per second squared, and we want to find the displacement here. Which of those group B equations, we know this is group B, so which of these group B equations seems like it might fit the best here?
I used VF squared equals VI squared.
Okay. VF squared equals VI squared plus 2A times delta D. Okay, I'm writing that down blindly because I know it's a valid equation. Before I write it down, I'm not checking to see if it's the right one. That's the one that you have in your mind. That's a valid equation. I'm going to write it down. I'm going to try it. Does it work? Do I have VF? Yes. Do I have VI? Yes. Do I have A? Yes. Do I have D? Well, no, but that's what I'm looking for, right? So that's okay. How do you rearrange that to solve for D? Is D on the top? Yep. So now I just got to follow my rules, right? What are my rules? What's the first rule? Get rid of what's not attached. What's not attached? What's not attached to this? VI squared. So how are we going to take VI squared over to the other side? Subtracting, right. VI squared is added to 2AD, so we're going to say VF squared minus VI squared equals 2A times D. Remember, we're solving for D still. Now get rid of what is attached. What is attached to D? 2A. So let's take it over by dividing. It becomes VF squared minus VI squared. Remember, we divide the whole thing on the left by 2A. And I end up getting VF squared minus VI squared over 2A is equal to delta D. So let's sub some numbers in here now and see what happens here. Delta D is VF squared, 27.7778 squared, minus VI squared, 13.8889 squared, over 2 times 3.8. Okay, let's do that together on the calculator here. Now, what did we say here yesterday and the day before in terms of doing things on your calculator? Do what's on the bottom first. So let's say 2 times 3.8. The bottom gives me 7.6. Now let's do what's on the top. 27.7778 squared minus 13.8889 squared equals, and then let's divide that number, 578, by the number we had on the bottom, 7.6, gives me 76 meters. And that's the answer that's given to us from the book. So 76 meters is how long this needs to be. Now, realistically, if you're an engineer designing the highway, you're probably going to make it longer than 76, right? 76 is not the number. 76 is the minimum length that it needs to be in order to accomplish this, right? You get that person that is not so assertive when they're driving, right? You need the longer merge lane in order to get up to speed and to not cause a traffic jam. All right, here's another question that we're going to work on as a group here. Unfortunately, I don't have this one copied for you or anything. I'm going to ask you to copy this one down, please. But it's the only one that I'm going to ask you to copy down. So this question says a 1,600 kilogram car begins at rest at a stop sign, then accelerates 4.0 meters per second squared for 5 seconds, and then travels at a constant speed for 34 seconds, and then slows to a stop at 8 seconds. How far has the car traveled? What you got to recognize in this question is that there's more than one thing going on. There's an acceleration, and then there's a constant velocity, and then there's a deceleration. So what I want to do is break this up into stages. Write down my givens according to stage. Stage number 1, we're going to say that it begins at rest. VI is 0 meters per second. The acceleration in stage 1 would be 4.0 meters per second squared, and it does it for 5 seconds. So this is all stage 1. This is all as it accelerates. Then, and then is an important word because it tells us something different is happening. Then we travel at constant speed for 34 seconds. So I'm going to say in stage 2, it's traveling at, well, I don't know what the speed is or anything about it other than it travels at that constant speed for 34 seconds. And then finally, then again, in stage 3, it slows to a stop in 8 seconds. So we're going to say in stage 3, the time is 8.0 seconds in stage 3, and the final velocity in stage 3 is 0 because it's slowed to a stop. In problem 1, the blue one, I'm going to say that's a group A, sorry, a group B problem. In problem 2, it would be a group A because I'm traveling at a constant speed for 34 seconds, right? So we're going to make this a group A problem. And then when we decelerate or slow down during the 3rd stage, we're going to make that a group B problem again. We want to find the total displacement here, how far it goes in its entirety. What we want to do first is find the displacement in each stage. And then, of course, once we find the displacement in each stage, let's just add them up. So let's put in our equations here again, just so we have them handy. Which equation do you think you want to try for the 1st stage? Here, let's put this up here now, actually. Which equation for the 1st stage? Keeping in mind that we've got to choose from our group B equations, and knowing that there is no wrong answer if you choose from our group B equations here. Which one? Yep.
Looks to me like you want to use delta D equals VI times T.
Okay. So let's try D is equal to VIT plus 1/2 AT squared. We have VI. It's 0. So I'm just going to cross that off. 0 times time is 0. Plus 1/2 of 4 times 5 squared. Okay, it looks to me like we're going to use that one as well. 5 squared is 25, times 4 is 100, times 1/2 is 50. So there you go. I got the displacement for the 1st stage already. Yep. Yep. Now, what about the 2nd stage? We have only one option here, right? For the 2nd stage, I guess which makes it not really an option if we have only one. We have only one thing to try here for the second stage, and that's going to be this one, our group A equation. V is equal to delta D over delta T, or D is equal to V times T. But my problem is I don't know what V is. Any suggestions? Any suggestions there to find V? Yep. Good. That's exactly what you do. Very good answer. In the first stage, there is a final velocity. We don't know what it is, but there is a final velocity. Now, in the second stage, whatever my final was from the first stage is going to be my constant velocity for the second stage, right? If I speed up from 0 to 5 meters per second, and then I go at a constant velocity, I'm going at a constant velocity of 5 meters per second. Let's figure out what VF is for the first stage, and then make that the velocity for the second stage. How do you want to find the final velocity in the first stage?
Would it be the displacement we just found over the time?
No. Okay, good try, but that doesn't work. Why could we not say displacement divided by time in this first stage? Why is this wrong? We just got displacement, we have time, why is that wrong? Yep.
Because we accelerated through there.
Okay, so stage one was acceleration. It was a group B problem, and that's a, what equation is that? That's group A, right?
Yeah.
Let's erase this. Can't use it. Group A equation, group B problem. So what do you want to try now if that equation doesn't work for us? Remember, I say try things, right? Don't try invalid things. Don't try V equals D over T. That's going to get you the wrong answer. Sure. Sure, let's try that. VF squared is equal to VI squared plus 2AD. VI is 0 here. We solve for VF here. It works out to be the square root of 2AD. So it's square root of 2 times 4 times the displacement of 50. Square root, what is that, 100, 400? I think it's 20, isn't it? I think it's exactly 20. Okay, there you go. Now look, the time is 34 seconds. My constant velocity is 20 meters per second. Remember, my final velocity in stage 1 was 20. My constant velocity in stage 2 is 20. So let's multiply my 20 meters per second by my 34 seconds. That gives me, I think it's 680 meters. That makes some sense? What about stage 3? Stage 3 involves deceleration. Is that group A or group B? It's group B. Yeah, group B. So pick an equation from group B to try to solve for displacement. What do you know in group B? Sorry, what do you know in the third problem here? We know the time, we know VF. Is that it?
We know our initial.
We also know VI. VI is 20 meters per second. At the end of stage 2, it's moving at 20. So at the beginning of stage 3, it's moving at 20. Now we know VI, we know VF, we know T. Which one do you want to try here? Josh, which one do you want to try there? VI, VF, T, group B problem, right? So which one do you want to try? Good, that's the one I would try as well. D is equal to VI plus VF over 2 times T. So we get 20 plus 0 over 2 times a time of 8. That gives me, I believe it's 80 meters. Now, you want to find the total displacement here. Let's just add them up. Remember, there's 2 ways to find displacement. Remember, this goes back to day 1 of Physics 20. Either add displacements or subtract positions. Well, we have 3 different displacements here, so what are we going to do? We're going to add them up. Right? We got 50 meters plus 680 meters plus 80 meters. What does that give me? 730, 810? 810 meters.